Hey folks, welcome back to another Geometry Nodes tutorial. In this one, we're completing our series of doing stuff with collections and curves. So previously, we've had a look at bending, deforming objects along a curve, individual objects. And then we've also had a look at how we can create an array along a curve and then deform that to a curve. And that added a little bit more complexity to it. And now we have the sort of the third part of this idea, where rather than an entire collection, what we're going to be doing is picking an object from a collection and instancing one object per curve. Not deformed, just basically creating an edge, a single edge, and instancing on that edge with our object scaled and rotated to align to the edge. There's a little bit of additional logic in here for us to make it into a sort of a higher level tool. Shout out to Panic Carefully for suggesting this one. And also just if you ever feel like you need to do something in Geometry Nodes and you're not sure how, go and check on the Discord server, linked down in the description, because there's always people on there helping people do Geometry Node stuff. So big community, very active help channel. Let's have a look at what this tool is and isn't. So on screen now, we have the result of the instance on edges node that we'll be making today, instancing an I-beam on Suzanne. Important, if we look at our spreadsheet, we can see that these are instances. This is not geometry, or it's not realized geometry. And we're just sticking and scaling one instance per edge here. We can translate these locally. So for example, if I move them in the Z-axis, you'll see that they move along that edge. If I rotate them around their Z-axis, they rotate around their local Z-axis. And if we rotate them, for example, around the X-axis, again, it's their local X-axis, but you'll see that they're rotating around the middle. This is something that's important because if we have a look at the actual I-beam, the origin is at the bottom. So you would think that it would rotate around that position, but we've been able to create a custom pivot point, which I've set to be the middle of our spline, and you'll learn to do that later on in this tutorial. You'll notice that all of these have been scaled evenly, so they all have the same radius. But we can also set it to be proportional scaling, in which case they will just match whatever size the original had or the ratio, the aspect ratio of the original object, and it will just be scaled to fit. Now what this is not is bending. So this is the result of the curve deform grouped nodes group, which is from our curve deform tutorial, one of the previous two. And this one you can see is actually deforming to splines instead of just being straight edges. And if we look at our spreadsheet, no instances on this one, and we have what's this, 1.57 million triangles versus the instance on edges, which is technically the same amount of geometry, but because they're edges, we only actually have 3,200 triangles. I am in Blender 4.1 here. Let's jump in, and we're going to just start off with a monkey mesh Suzanne. And I'm going to add a new collection up here, pressing C, and I'm going to call this one objects. Now let me just hide Suzanne for a second, and let's add some objects. We're going to be adding a couple of UV spheres, and let's just scale them in the Z-axis. Doesn't matter what size you really go for here, let's apply the rotation and scale. And I will also just select a few of the faces coming down here. In fact, let's do it in the positive Y-axis. Like this, and we'll just extrude those out. Something like this, just to give it a bit of a fin so that we can deal with the orientation later. Something like this when you're making an object for building a tool. Sure, it's useful to do the actual objects that you're going to be using, but it's also important to learn how to make kind of debug objects and the things that you're going to be looking for. So for us to ensure that we have the right control, I want to make sure that this is an atypical size. So if we have a look at our item size, this is 3.18 meters. It's just random dimensions, basically. That's much more useful than having something which is exactly 1 meter across or 2 meters across, because that is going to potentially cover up errors in your system. Equally, let's make a second one. I'll make it a different size. And if I tab into edit mode and I'll move it up, now you can see that this one's origin is not in the middle of the geometry, whereas this one is in the middle of the geometry. So we want to make sure that in our case here, if we have an edge, it's always going to place our little rugby ball here on the edge, regardless of where our origin position is relative to the geometry. So a few things that we can build into our objects here that just guarantee that we're building a robust and useful system. Back to geometry nodes, we only need these two really. I'm going to hide that objects collection, go to my Suzanne object, make a new node tree, and I'm going to pin this because we have multiple objects. Let's bring back our Suzanne object visibility. And where do we start with this? Well, the simplest way to start is with a mesh to points node. So mesh operations, mesh to points, and we will be turning the edges into points. We can then simply instance on points our objects collection. We'll turn on pick instances and we'll separate and reset the children. Okay, so this is pretty good, but obviously there's a lot still that we need to do. We need to deal with scale and we need to deal with rotation and we need to deal with position because some of these are offset from their origins. So what information are we interested in? If we come into mesh read edge vertices, then we have position 1 and position 2. And actually I'm just going to view my mesh to points node. If I use a mix vector on the position 1, position 2, and I just plug this into mesh to points position, now each edge is defining the position of the point that gets generated. And you can see as I change my mix factor, we're moving between position 1 and position 2. So this is essentially the idea that we're going to be using for how we position our points. And then we can also do position 2 subtract position 1. This is going to give us the direction of the edge, the vector along the edge. And we can also do the vector distance to find the length of the edge, and then we can scale to it. So fundamentally, this edge vertices node is going to be what we're interested in using. However, we're not going to be doing all of this stuff before the instance on points node. We're going to be doing it afterwards to the instances. It's a little bit easier for us to kind of compartmentalize the tool, makes it more readable, which makes it better for your teammates, makes it better for you coming back to it later, and just generally makes it easier for us to work with. So what we're going to be doing is, rather than manipulating all of our data beforehand, we're simply going to be storing the positions of vertex 0 and 1, or position 1 and 2, onto our edges. It needs to be edges because it's the edge domain that gets maintained when we do a mesh to points with the edge domain. So let's grab a store named attribute node. This one is going to be called v0 for vertex 0. It will be a vector on the edge domain with position 1. Then we will use another store named attribute with a new attribute called v1, and this one's going to be using position 2. Let's hide those extra sockets. Okay, so now when we do our edges, let's have a look at our spreadsheet and our points. You can now see that we have v1 and v0 in our spreadsheet, so we have all of that data that we can now use on our instances as well, because these inherit it when they get instanced. Now, for us to be able to actually scale these down, I need 2 bits of information. One, I'm going to need the length of the edge that each one is on. We have that information now. But the second piece of information that we're going to need is the size of our actual object. Right now, we don't know what its bounding box is, and so we're going to need to create a bounding box. Now, you may have one of these bounding boxes if you followed along with one of my previous tutorials on custom bounding boxes, link down below. Or let's go through and actually build it now, because it's not too complicated and we can just kind of run through it. If you want more information on this process, I recommend you go and watch that tutorial. We're just going to be kind of flashing it here so that you get a sense of what's going on. Let's have a look at our collection info, and actually let's just look at the collection info. We've separated and reset our children just to make sure that they are at their origin equals 0, 0, 0 position. And then we're going to use a bounding box node. This is going to give us a bounding box per instance. On each one of these bounding boxes, I want to know what its minimum and maximum size is. And so the way that we're actually going to do this is not with the min and max values here, because as you can see, if we look at these, they're both reading zeros. And if we go into the instance domain, again, they're still reading 0. So these do not evaluate correctly while we're dealing with instances. Okay, so what we need to do instead is let's use the position. And you can see that the position node is working correctly. And then we're going to use an evaluate at index node. Set a vector on the point domain and index 0. You can see that as we're drawing this, we're seeing index 0 has a value. And then we have 1, 2, 3, 4, 5, 6, and 7. And 7 is the top right corner, 0 is the bottom left corner. That's always the way. These are generated in a very specific order so that the first and last points are the min and max positions of our bounding box. So evaluating the position at index 0, let's capture this as a vector on the point domain, like this. And equally, we're going to grab another capture attribute where we take the position evaluated at index 7, and we're going to be storing that. Okay, so we have all of this information on the bounding boxes, but we don't have it on our actual instances. For us to move it over, we're going to want to sample our bounding boxes onto the instances. We have the same number of boxes as instances, but as soon as I realize my bounding box, in order to have access to that data, because it's on the point domain, then I'm going to have, many, many more points, because these bounding boxes have 8 points each, than I have instances. So what we can do, because we have this data flat as a constant across all of our points here, we can simply delete the geometry with our selection just being the index, meaning that only the first point, as in the 0th point, will be saved. Now you can see that we have 2 vertices. Each one has all of its data about the min and the max. We've realized this. We can sample index, again using the index, and our value is going to be a vector. First one can be our max value, and our second one can be our min value there. Let's go ahead and just quickly rename these. So this one is max and this one is min. And now if we have a look at our instances, we can see that our max and our min are transferred correctly. Let's just capture this attribute as a vector on the instance domain. We've got our max here. And again, we have our min. And then we can just take these nodes. Let's leave our collection info node on the outside. Take all of this. Let's delete that viewer as well. Control G, put it into a new group. And on the outside, we're going to be plugging our geometry, which will be instances. So instances in and instances out. And then our first one is going to be the min output. And then the second one there is going to be our max. Okay, so that was fairly quick run through there. But again, this has been all covered in another tutorial. So do check that out if you're interested in a little bit of a deeper, slower process. Let's rename this one to bounding box per instance. And I'm going to clean this up, right click, show hide node options. And there we have it. Great. Okay, where are we? Something that happens with an instance on points node, which is kind of annoying and unfortunately hasn't been changed yet, is if I store a named attribute here, let's say I'm storing a vector, let's say I'm going to be storing this minimum, and I call it min, and then I instance it on these points. Well, these instances, even though it's this, which should have that attribute, if we look at the spreadsheet, it doesn't have that attribute. It doesn't exist on the mesh. If I realize them, does it show up? Because it was on the point domain, so maybe. Well, the attribute is now here, but it's all just zeros. So it's not actually being preserved, which is such a shame. If I change this to instance, then it just entirely disappears. And if we go back and remove our realize instances, it's just not there. So this is not an option, unfortunately. What we need to do is we actually need to transfer the min and max to the points of the mesh. Now, something that you might be thinking is, how do we get the correct min max value to the correct edge point up here? Because, if some of these are going to have one mesh and some of them are going to have a different mesh, then how do we make sure that those are always going to match up? Well, we can use the instance index here with a little bit of maths. So let's say that we're going to be randomizing our instance index. And I want to make sure that I'm using the correct values in here. So let's use values with a domain size node of our instances between 0 and, let's say we have 5 instances. We're going to need 0 to 4 as our values in here for indices. So let's subtract 1, and that's going to give us our max value there. So now that we know which instance index is which, we can now sample index from our instances based on this random value, and the value is going to be the vector min and max. So just the same connections, but min and max. Let's connect up our instances. Let's check our instance domain. There we go. Fantastic. So everything is working correctly. Let's make our lives a little bit easier as we work through here. We're going to be using some more store named attribute nodes. So let's grab a couple of these. We need one for min, one for max. This is going to be on the point domain for both of these. Call one min and the other one max. Connecting from our sample index nodes for the min max values. And now all of our points get the value. The instances then inherit this value back onto them. So now every instance has its own bounding box data. Okay, we've got everything that we need for the first thing that we'll be doing, which is scale and then rotation. So let's start out with scale. We're working after the instance on points node. We're going to be using a scale instances node. And let's just think about this logically. If we have an edge, and let's say it has length 4 meters, so a value of 4. And let's say that we have our object, and we're going to be aligning to the z-axis here. And let's say that the z-axis length is 2 meters, or a value of 2. We would need the scale of this object to be 2 times bigger for it to be the right size for this. In fact, if it was only 1 meter long, it would need to be 4 times bigger. So the maths that we need to do is the edge length divided by our object length. So the edge length here is 4 divided by 1 equals 4. The edge length is going to be the named attribute v0 and its distance to v1. So we can just take a vector math distance. This is our edge length. And then we need to find the length of the z-axis. So not the bounding box min max, but specifically the length of the z-axis of our bounding box. So let's grab these nodes again. We're going to be doing a min and max, and we're going to change this to subtract. So rather than it being min subtract max, we need max subtract min. So cross those noodles, and that will give you the length of your instance. Then we can use a separate XYZ node, and now we have the z-axis. Collapse that, frame this up with Control J, F2, this way is instance length. If we have a look at these, our instances now, there's a bit of visual glitching there, but our instances know how long each edge is, and they also know how long each instance is. If we take our edge length and we divide it by the instance length, now we're going to have the scale. And in fact, we can just plug this straight into the scale value of our scale instances node. And now this is feeling a little bit better. Obviously a lot going on. Let me turn off my wireframe drawing. But if you know Suzanne, you can see that this is more or less correct. Things look a little bit longer on the top and short in the eyes, short in the nose. It's looking okay for what we're up to. Okay, for now, this will do for our scale. We will come back and revisit it a little bit later. So let's deal with instance, or let's just deal with scale here. Okay, the next thing we want to do is going to be rotation. So let's grab a rotate instances node. And again, we're dealing with the local space. This time we're interested in the edge direction. So grab a named attribute node. And again, we're going to be looking for v1 and v0. And we're going to subtract V0 from V1. So it's important that you do it in this order because it needs to be the direction along the edge from 0 to 1. So we're going to be subtracting 0 from 1. We can then just use this with an align Euler to vector. This will be our vector. We're going to be aligning in the z-axis, and this will plug into our rotation. And already things are looking pretty good. In fact, let's simplify this. Let's take our objects collection, and the one that we made that was offset, let's just remove it from that collection and hide it for a moment. So when we're dealing with the one that was centered, all of our points are centered on the edges, and so we can see that this is lining up very nicely. One thing I would like to do is also control the rotation of this to align to the surface normal. So we need to know what that surface normal is. Before we do mesh to points, because the normal is derived from the faces, so we need face data, let's store on our original mesh, on the edge domain, because we're doing edges to points, the vector, which we will call norm. We're going to be storing the normal node. And if we now come back to our aligns, let's make a new align Euler to vector straight afterwards with the named attribute norm. This will be our vector, will be in the y-axis, and we'll be locking the z-axis because we've already defined that. So there we go. Now everything is sticking up nicely from the surface. This looks good. This looks perfect. While we're looking at this, actually let's frame these up. So the V1 subtract V0, this is our edge direction, and all of these together, these are rotation. Let's just hop back into our scale briefly here, and rather than using the divide directly into that scale, let's give ourselves an option. So we're going to use a utility switch node. On here, it will be a vector switch. We're going to plug our divide into the true socket. And in the false socket, we will plug the divide through a combine XYZ. Combine XYZ just basically allows us to only set the scale in the z-axis while we then control manually x and y. And you can see therefore that we're giving us a bit of radius control. So if you want to have a radius control, this is how you would do that. Let's just leave this as it is. You can always switch back to the proportional scaling if you want. But yeah, I'm going to keep mine like that for now. So we've done rotation and scale. That was very quick and easy. Let's have a look at translation next. So let's get our offset object back into that objects collection. And you can see it makes a bit of a mess. So all of our points are kind of moved around. And actually, I'm going to go back to the start of my node tree. And I'm going to add a grid node. So mesh primitive grid. And I'm going to use this instead for a bit. So all of the size is correct. In fact, I'll even simplify the grid further. So all of the sizing is correct, but they're just offset. So let's think about how we're actually going to work this out. If we take a set position node, and do you remember what I did earlier by plugging that mix node into the mesh to point node position? We're going to do the same thing here. So let's use a mix set to vector. We're going to be using the named attributes V0 and V1. And because we're working on instances, if we set the position, it will just move the whole instance. And that's what we're after. So now we have a bit of control in here. Fundamentally, we need to know how far along the edge, and if we turn off clamp factor, then we can use a value in here as well to go beyond. So with clamp factor, it will just lock to that 0 to 1 range. Turn off clamp factor, and then you can extrapolate beyond. So interpolate is between, extrapolate will go beyond. Let's have a sketch so that we can understand what we're up to. I have a rugby ball shape. It has an origin. Some of them are in the middle, some of them are below. I want to know, as a proportion of the length, because we want the length to be a 0 to 1 scale, basically to align to our edges being 0 to 1, right? Because we're interpolating between 0 and 1. We're basically positioning it based on some proportion of that length. I want to know if the bottom of our object is at 0, what, as a proportion of the length of the object, the distance from the bottom of the object to the origin is. Okay, and the way that we can work this out is if we know how long the object is, which we have with max minus min, if we have this for our length, and we also have the min value, then we can work everything out, right? So let's say that the minimum point here is at -1, and our object has a length of 2. So max minus min is equal to 2, and min is equal to -1. That would mean that the origin position is 1 meter above the minimum position, right? Because it's centered, it's above it. Now, if we work this out as a proportion, how do we make 2 into 1? Well, we would divide it by 2, right? And it's not just that it's 2, it's that it's this value. So if this was 3, it would be divided by 3, okay? So let's say this is 2. We're going to divide everything by the length of the object. So this becomes 1, and this becomes -1/2. Now we just need to multiply it by -1 because it's actually going in the opposite direction. So times -1 is going to be equal to 0.5. And that would make sense. We have our origin in the middle, and so the interpolation wants to position our object in the middle of the edge. Let's throw in some different numbers here. So we're going to have a length of 2 again, but this time our origin position is below the minimum, in which case our minimum value would be something like, let's say 0.2. If we divide everything by 2, then we have 0.1. This needs to be multiplied by -1. And that's going to give us -0.1. So hopefully that makes sense. We're basically working out as a proportion of the length what the distance from the bottom of the object to the origin is, whether above or below. So how do we work this out with actual nodes? Well, let's take a couple of named attribute nodes. We have our min and our max, and we're going to be subtracting from the max our min. So that is going to give us the vector from the bottom to the top of our object. We can then divide our min value by this length. So let's divide our min by the length. Now, because we're doing this with vectors, it's happening in all 3 channels simultaneously, but we can just separate out our z value at the end. Now, the final thing that we did was we multiplied this by -1. So we inverted it to push down. So let's take another vector math node, set this to scale, and we will set this to scale by -1. Now we can use a separate xyz, and we can just use, if I show this, get rid of that value node, let's use the z value in here, and you can see that those just fix themselves instantly. So now it doesn't matter. So move these around and you can actually see, let's scale them down a little bit. So if I grab one of these and I move it up and down, it's not going to affect, even though it's moving relative to its origin. So moving in other axes will affect it, but moving in the z axis, we're fixing the z axis so that it always works. I'm going to take all of these nodes, Control J, put them into a frame, F2. This one is translation for our movement. Okay, let's do a little bit of cleanup here at the end. We've got our instances, and we can see that we've got loads of attributes: norm, min, max, v0, v1. We're going to keep v0 and v1 just in case you wanted to do something with that for some reason. You know, it might be data worth keeping. But what we're interested in here is simply removing with an attribute, remove attribute. We're going to be removing norm, we're going to be removing max, and we're going to be removing min just at the end here. Then what we can do, let me erase those, and we're going to take everything. So we're going to keep our objects and our collection info node at the beginning. We're going to select everything that we've just made, Control G to put it into a new group. Come back to the beginning here. We are outputting instances. We are inputting a mesh, and our input that comes down to the bottom here, this is also instances because that's coming from that collection info node. This node group is going to be called instance on edges to match the naming convention of instance on points. And then we need to do a few things. So this should feel kind of similar, kind of native, right? It should feel like the instance on points node. So let's bring a few bits of familiarity here. So we've got mesh, and then we can do a selection. This will actually be on our mesh to points rather than the instance on points node. And just to match our instance on points node, let's pull that up above. Then we can also bring in pick instances. This will be turned on by default in this case. And we also want our instance index. Now we've set this up with a random value. Let's actually adjust how we're doing this. So we'll use the instances and we'll use a truncated modulo. Let's bring a new socket for our instance index, just so that we capture that name. And then we will pull this into our truncated modulo, right? So we're taking the instance index that we feed in, which by default, we can set to be the index. Now by default, when this instance index goes to the instance on points, it automatically loops. So if you plug in a value of 100, but you've only got 2 points, then it will remap that to be either a 0 or a 1. They're the indices that you have available. It's already doing a modulo on the indices. We need to do it manually for these sample index nodes. So we will just plug our instance index that we made before through that truncated modulo. And then if we come back to the front, let's use a random value node, integer. We will plug this on to that instance index. The next thing we want to do is deal with this normal value, because you may wish to define the normal specifically. Rather than having the normal on the inside, we will plug a new value into our store named attribute, which I will call surface normal. And by default, this will just be the normal vector. So if you have a mesh with faces coming in, this is going to behave exactly the same with this unplugged. However, it just means that we can override it with something custom. If, for example, you're using curves or splines and you're drawing on a separate surface, you want to sample the normals from that surface into this node group. Let's continue adding a little bit more controls. We can see on our instance on points node, we add this rotation and scale stuff. So we're going to need a transform section to deal with that. Let's go ahead and add a new panel, which will be called transforms. In here, we're going to be controlling our scaling amounts. So we have this vector switch, which allows us to set this to proportional. So go ahead, add a new socket to that switch, which we will call proportional scaling. And let's drop this into that transforms group. And then we will also add a new input, which we will call scale. You could call it radius or whatever you want, but I'm just going to call it scale. Plug that into both your combine XYZ, X and Y. Now if we come back, you can see that we can set this value on here. I might set my default to be 1 just to make sure. There we go. The next one we're going to deal with is translation. Let's grab a new group input, and we're actually going to do this right at the end after our rotation down here. So let's grab a translate instances node. This will be set to local space, and if you move this in the z-axis, you can see that things move there. So let's set this back to 0, and we're going to just connect a new socket onto that translation, and we will drop this into our transforms as the first object. If we were to look at something like a transform geometry node, you can see it says translation, rotation, and then scale. So we're going to be putting rotation controls in the middle here. So we will need to do one more thing to the translation, but I want to be able to demonstrate it before I show you. So let's deal with rotation controls now, because this is actually a little bit tricky. So after our rotation, just as a separate one here, let's throw in a new rotate instances node. And if we have a look at this, let's rotate it in the x-axis. All of the ones which have their origin in the middle, they're fine. And in fact, let's just make this a little bit more difficult. Let's move this so that they're all a bit off-centered, right? So now you can see that if I move these, they're not rotating around their centers, and we really want them to. We want them to move around their centers. We know where the centers are, right? We can go and find the middle position with a mixed node, set a vector, between the named attribute v0 and v1. If we set this as our pivot point, well, that's not quite right. But if we set it to local space, then you can see that these are actually now rotating around the correct point. However, while it's global, our pivot point is global, but unfortunately our rotation is also global. So what we really want is a local rotation with a global transform pivot. So that's a bit of a pain to deal with. So what we're going to do instead, this is going to seem a little bit counterproductive, so I hope you'll bear with me. We've done our rotate instances to put them into position, right? And if I mute that, you can see that they're all sorts of random positions. If we were to then take our align Euler to vector, and we were to pass this through an invert rotation node, one of our new rotation nodes, and just plug that into the rotation of our rotate instances, then you can see that we've now aligned these to the global axis again. So we've rotated them with their original rotations around the specific pivot point, right? And if I mute both of these, you can see that they stay the correct orientation, but they move. And that's because of this transform that we did before. So this is fixing the origin positions. This is rotating them into position. And then this is re-rotating them around their new centers that we want to define. If I was to then use a rotate to rotation node on here, and this can be set to global, I can rotate things around the z-axis, around the y-axis, around the x-axis now, and they're all rotating around that local pivot points. That's all well and good, but we need to fix the rotation. We need to put them back onto their edges, right? So let's take another rotate instances node, again with the same pivot point, and this time taking the original rotation once again into the node. So it's a little bit convoluted again, I'm sorry about this, but it does allow us to actually control our rotation very specifically. So now you can see I can rotate things around what feels like their own local axes around a pivot point that we've actually been able to define as the center of the edge. So it's just a bit more intuitive. It feels correct to use this now. Quick editor's note here. This second rotate instances node is not necessary. Let's go ahead and get rid of that, get rid of those reroutes, and we're actually just going to use a second rotate rotation node with our original rotation coming through like that. This way we're keeping everything within fields versus using a second geometry node here, and it's just going to be a little bit faster, a little bit more performant as we work on. Let's put this into a frame. This one is going to be rotation offset. And we need to control this rotation on our node group. So let's grab a new group input. We're going to take a new socket into that rotate by. And we will just drop this after our translation and call this one rotation offset. So now if we tab out, we can set all of our rotation offsets in here. We have our proportional scaling and our horizontal scaling there. Actually, our scale never wants to go into the negative. You can see that's the problem. So let's just fix that. That scale has a minimum of 0. There we go, that's better. Set that back to proportional. So yes, all of our rotations are working. I want to show you one thing that we need to fix about the translation. And to do that, we're going to need to make some of these a bit smaller. And then we turn off proportional scaling. And then if we now translate in the z-axis, what are you noticing here? The ones that are really short move less fast. In fact, they all move at a different speed. And this is because the translation that we added at the end here is in local space. So it needs to be in local space because they need to move where they've been rotated. But because it's local space, that space is also compressed by the scale. And in this case, you can see that they're much wider than they are long. Therefore, the speed they move in this direction is very slow. How do we fix this? Very, very easily. We simply need to divide our translation by the scale that we applied before. Let's take this scale value through a reroute just to grab it to the end. And we will simply take a utility vector, vector math divide by that scale value. And now our translation is relative to the scale of the object. So this is all now working. Rotation is still working, but now the translation feels, again, it feels correct. Set that back to 0. There we have it. This is the tool. There's quite a lot in there. I know I just went through that quite quickly, so hopefully it was all right to follow. So this one's super fun to play with as well, because if we were to now go in here, and let me show you how to set this up with a curve so that you can draw with it. If I add something simple, let's add a plane. Bits of definition just so that we have something on here. There we go. And then I'm also going to add a curve, just a Bezier curve, and I'm going to tab into edit mode and I'm going to delete the vertices. Then if I press T, I can bring up my side panel and I can go into the freehand drawing mode. And if I press N, it goes to my tool menu, then I can say that I want to draw on the surface. So projected from the camera view, whichever surface it sees first, that is the surface you will draw on. You might have your tool options along the top here. So I can now draw some edges like this. And you can see that they're fine. They sit here where I drew over the object. We've got some squiggles in the middle. That's all fine. It doesn't matter at all. Let me actually just hide the plane so that we don't have to see it. Back into my node tree here. We want to bring in our plane object and our Bezier curve. And I will actually just hide both. Looking at our Bezier that we have in our node graph, if I simply resample this curve to a count of 2, now I have a straight line between start and end. And then I can just do a curve to mesh. And now I have a mesh that I can use instead of my group input. Let me turn on proportional scaling, and there we go. Now we don't have any normals from our geometry which is coming in, so I want to define my normals manually. So let's take our object info with the plane. We are going to sample nearest surface, a vector, the normal, and I actually want to sample the normal in the middle of each one of these edges. Because if I sample it right now, it's going to sample onto the points and then it's going to interpolate across. And while that should be correct, I think, I do just like to have the confidence of knowing that I've defined it. So let's use an edge vertices node. And we will just mix from 1 to 2, 0.5 as the sample position. And now I can just guarantee that each one of these edges is only using its middle position to sample the normal. Also, if you have undulating surfaces, you might want to specifically know where the middle is, because that's ultimately where we're going to be instancing visually our object. This now becomes our surface normal, so we can plug that in there. And you can see that these have rolled over nicely. Let's bring back our plane object and our Bezier. Let's bring this up. Tab into edit mode on our Bezier. Let's draw some horizontally, and you can see that they're following that curve on that surface. Isn't that neat? If we grab our move tool, you can see that as I move these around, they are working appropriately. That's about it. That's all I got for you today. This was the final section of our Put Stuff on Curves series. This is a super useful tool if you're into stuff like kit bashing or architectural structures, engineering things, a load of hard surface stuff you can do with this as well. Yeah, it's a great process, very easy to work with. And especially if you've followed through with the other tutorials that we did on grouped curve deform, that was the first one I think, and then collection of objects along a spline with like a deformed array. They're just very useful tools. All of these three in conjunction can be used to great effect. You're basically enabling yourself to put anything anywhere, and doing it this way, we're keeping this as instances, right? These are still instances. So no matter how many you have, it'll be super lightweight for you to render, especially with cycles, and just generally processing them will be fairly straightforward. And because we're doing non-linear scaling and fun little transform tricks, we're able to get a system which is very robust and flexible, even though it's still an instance. So there we have it. Hopefully you had fun, hopefully you learned something, and I'll catch you in another one real soon.